So folks, in our last video, two videos ago, we defined what it meant to be a critical point. And then in the most recent video, we went ahead and found the critical points of this function right here. What we eventually want to do is classify these critical points, the 5 points that we had, 0, 0, 2, 0, 0, -3, 2, -3, and 1, -3 halves, as either local minimums, local maximums, saddle points, or whether maybe we can't determine at all because our test is inconclusive. So jumping on to the next page here is the second derivative test that we get in Calc 3 for these types of functions. We'll discuss a little bit about where this test comes from in class, but for right now, let's just take it as a test that we evaluate those critical points in to determine what type of points we're dealing with. So here's our second derivative test for functions of two variables. Suppose the gradient of f is 0, and by the way, that only works for these types of critical points, the critical points we get from when their gradient's 0 and not where it was undefined, and that the second partial derivatives are all continuous around the point that we're checking. So we define what we're going to call the discriminant, or another way to say it is the determinant of something called the Hessian matrix. We'll discuss that in class. But we're going to define the discriminant by this function right here. Notice that we're using d for discriminant, and it's composed of all of our second partial derivatives combining in this particular way. We'll discuss why we combine it this way in class, but here is our formula, and then we get to interpret it. If, when we plug in some ordered pair a comma b into the discriminant function, it comes out to be positive, then we know that we either have a local maximum or a local minimum. Whenever the discriminant comes out to be positive, we're going to have one of those two cases. If the discriminant is negative, then we know we've got a saddle point. And if the discriminant equals 0, then the test is inconclusive, and we'll have to determine what that critical point is by some other means. This is equivalent to in Calc 1 when your second derivative test failed. So let's just look at this further. We said that if the discriminant comes out to be positive, then it's going to be either that we have a local maximum or a local minimum. To further check that, what we have to do is we have to look at the second partial with respect to x, evaluate at that point. Technically, we could also do the second partial with respect to y. You could also be checking fyy of ab. It doesn't matter which of those two you check. Usually we just check f sub xx. So we plug in the critical point into the second partial with respect to x both times. If that comes out to be negative, as well as the discriminant being positive, then that's how we know we have a local maximum. If this second partial with respect to x both times at the critical point comes out to be positive, and our discriminant was positive, then we've got a local minimum at that point. And again, we'll give some intuition for why this is so when we get to class. So folks, here are the steps for finding all of your local extrema and saddle points for a multivariable function. You're going to first classify all of the critical points. So find all the critical points to the function. Then you're going to classify them using the second derivative test, and separately explore any points where the test was inconclusive, or if the critical point was obtained because the gradient was undefined there. You get sort of some separate exploration to do in that last part. Okay, so let's go back to our function that we were just looking at. We saw in a previous video that the critical numbers for this were the ordered pairs. Folks, and by the way, sometimes I accidentally call these critical numbers. That's a very bad habit I need to get out of. These are critical points, not critical numbers. And we found the critical points to be the ordered pairs 0, 0, 2, 0, 0 minus 3, 2 minus 3, and 1 comma, was it negative? Yeah, -3 halves. So those were the critical points that we saw in the previous video. The next thing we want to do then is we want to plug each of these critical points into this discriminant and see if we can classify the critical point as either a local maximum, a local minimum, or a saddle point. Otherwise, the test is inconclusive. Let's see what we can do here. So we're going to need to construct d of xy, which we just said was going to be f sub xx times f sub yy minus f sub xy quantity squared. So in our case, if you go back and look at what we computed for our partial derivatives, we computed all of our second partial derivatives here. Let's take that information and we'll build the discriminant from that. This is going to be lengthy, folks, in our case, for this particular problem. But our d sub xx, we found to be 2y squared plus 6y. And then we're going to multiply that by f sub y, which we found to be 2x squared minus 4x. And then we're going to subtract from that our mixed partial squared. And taking what we obtained for that, we had 4xy plus 6x minus 4y minus 6. And that's quantity squared. So this is our discriminant for this particular multivariable function, this one right here that we're looking at. So what we now do is we go through and we classify each of these critical points. So for example, we could compute d sub 0, 0 into this, and if I plug that in here, notice that make my first expression is all 0, my second expression is all 0, minus, let's see here we'd have this term is 0, this term 0, this term 0, so we just have a minus 6 quantity squared, which gives us a negative 36. When the discriminant gives you a negative value, you're done working with that critical point. You have classified it as a saddle point. So 0, 0 is a saddle point. Again, we get that through this information in this chart right here. Since the discriminant came out to be negative, that critical point is in fact a saddle point. We could then check some others. I'll let you check the rest of these. Go ahead and check d sub 2 comma 0. For instance, plug that in. When you do so, you're actually going to find that it's negative 36. So that's going to tell us that we also have a saddle point at 2, 0. And then you can find also that we have a local maximum at this point, and you can go ahead and finish classifying these. So please go ahead and do so. So I'm just going to put you finish. And just you can check your work here in discriminant. Here you have the graph of this function that we can explore, or maybe a little bit easier to read is the contour plot for this function. But either way, notice that you can see that we do have saddle points. We have a total of 4 saddle points on this function at 4 of those critical numbers, and we have a local maximum here. Let's actually, even though I said you finish, I think I'd like to do the point that's a local maximum altogether. So let's compute d of 1 comma negative 3 halves. So if we did so, we would have to plug in the ordered pair 1 comma negative 3 halves into this expression. So let's do so. It would be 2. So when you compute this discriminant, you end up with a positive 9. Now, the reason why I wanted to do this example was because when the discriminant is positive, we at that point know that we either have a local maximum or a local minimum, but we have some more checking that needs to happen. So the next thing we need to do is we need to compute f sub xx of that critical point. And if we do so, let's see here, plugging 1 comma negative 3 halves into f sub xx, that would be 2 times negative 3 halves squared plus 6 times negative 3 halves. And if we compute that, what do we end up with? We end up with the value negative 9 halves, cheating and reading it from the chart there. And so since the discriminant was positive and the second partial with respect to x both times was negative, then we go ahead and classify that critical point as a local maximum. So the ordered pair 1 comma negative 3 halves is a local max. Okay, folks, please go ahead and finish this out. Check the, I think we've checked 3 out of the 5 points. I'll leave you to check the other 2, confirm that they're saddle points, and then go ahead and work to my math lab for this section. Thank you for your patience, folks. Let me know if you have any questions.